Okay, so as was said there, if you're doing the project, one of the really practical things you're going to have to do quite early on is to decide which software framework you're going to use to actually do the implementation. And thankfully nowadays we have an embarrassment of options really available to us. There's quite a lot of really good frameworks out there. 4 years ago there was virtually nothing available. You had to code all of this yourself, so now you have lots of options, so that's good. This lecture is just going to talk about a handful of those options, probably the most popular, well-used ones at the moment. There are new ones appearing actually every day. So I'm going to talk about some of the bigger packages: Caffe, Theano, Torch, TensorFlow, MixNet, MatConvNet, Nirvana Neon, and Leaf, in that order roughly. If any questions as I'm going along, please feel free to ask. So Caffe, or CAF, depending on where you're from, is a deep learning framework from Berkeley. It's probably one of the older ones that's been around for a while. It's actually based on another framework called DCAF, which was written in Python. They re-implemented it in C++, and it runs on both the CPU and the GPU. So most training nowadays you'll do is on the GPU, but people often want to do prediction on the CPU. So you might train a big model on a server that you have, and then you might want to put that model onto another server that doesn't happen to have all the GPUs. Maybe you don't want to pay the extra that you would pay in Amazon for the GPU usage, and you want to run it on the CPU. So Caffe runs on both, so that's one good thing about it. It has a Python wrapper as well, so a lot of the stuff you'll do with Caffe is with the command line tools. But if you're a Python user and you need to, train a model or extract features or extract some individual layers, examine them, this can all be done through Python. Its Python wrapper is not quite as good as some of the other ones out there, but it's usable. There are a bunch of command line tools that you will use with Caffe to do prediction. One of the interesting things about Caffe that's slightly different from all the other frameworks that's out there is it uses this kind of binary file format called Google Protobuf, which allows you to specify models actually in a text file and store models in a binary file. And I'll show an example of that on the next slide. And it supports kind of out of the box a bunch of different file formats that you might want to use for training. So you can load images from the file system from just folders. You can use two of these high performance key value stores called LevelDB and LMDB. I'm not going to go into what they are, but basically it allows you to stick a bunch of images into a really compact format and read them off the disk really quickly. So often with GPUs and things nowadays, the bottleneck is not necessarily in doing prediction in the model or even doing training. It's actually in the I/O, getting things off the disk and into memory quick enough that you can actually do your backpropagation step. That's how fast modern GPUs are. So if that's the bottleneck, having these file formats is good. It also supports the industry standard HDF5 format. So here's kind of what you would do if you're specifying a model in Caffe. So you write this kind of funny proto-text files to describe the architecture of your network. So in this particular example here, this is only a little snippet of it. This is just the top part of it, right? So we're defining a network called AlexNet. You'll see what AlexNet is later on. You have a layer, which is your input layer, and you specify, okay, this is going to be, here we have a batch size. You might hear batch sizes mentioned already. The batch size in this case is 10. We're doing images, RGB channels. We've got 3 channels there, and we're going to process images that have width and height. These are square images of 227 by 227. Why that, I guess you'll see later on in the memory lectures as to why you might choose these particular parameters. And then we're going to do a convolution, and Caffe lets you say, okay, well, the input for this convolution is coming from the data layer, which we just specified there. It's going to be called conv1, so other layers can refer to it. It's going to have 96 filters, kernel size of 11, and we're going to stride. So Lisa mentioned striding earlier on. We're going to take steps of 4 pixels each one, so we're going to reduce the dimensionality by 4 straight away. We can also set the different learning rates here. So this is saying that the first part here is the learning rate on the bias, or actually on the weight, sorry, and the second one is on the bias. So we're saying we don't want to decay the bias at all. We only want to do weight decay, which was this L2 regularization you seen earlier on. We don't want to do that on the bias. We want to let the bias go wherever it wants, but we want to keep the weights kind of small. We don't huge weights somewhere and small weights other places. So this is saying that this is the kind of regularization we want to use. And you keep doing that and you can build up a whole graph structure or a sequential model. And then once you've got your model specified, you need to give it another file called a solver file, which just tells it the parameters, the hyperparameters of the optimization. So So what's the initial learning rate that we want to use? How do we want to decay that learning rate over time? How many steps do we want to take until we do a learning rate decay? How often do we want to display the progress that we're making? All these various things, the actual weight decay parameter itself. Where do we want to save our snapshots of our model? So one of the things that you don't want to happen when you're training a model that's going to take 2 weeks to train is for your computer to crash halfway through it, right? Or even worse, after 2 days, and you don't notice until 7 days later, right? So one of the things that you can do is snapshot the model as you're going along, and that way you can resume training if it crashes. Or if you start to overfit and you haven't noticed you've overfit, you can just take one of the snapshots that you've saved to the disk and use that, and that's the early stopping thing we mentioned earlier. So to train a model with these sort of specification, you just go to your command line tool, say Caffe, train, give it the file, and off it'll go. It'll print all the information to the console, what the current loss is, what's the loss on the validation set, all of this information. And so it's quite straightforward. You don't actually have to write any code. Well, I mean, you can consider this code, but it's more of a specification. So that's one of the nice things about Caffe. So the pros, one of the things is it's got very portable models. So by portable, I mean I can train a model, I can give it to you, and you don't have to understand really anything about the format of the model. It's all specified in these proto-text files. So if someone else is running Caffe, they can just read it in and run it. And because of that, there's actually lots of models available pre-trained for Caffe. So there's a website online. If you type in Caffe Model Zoo, you'll find this page that has models trained for loads of different tasks: semantic segmentation, classification. You can download them, run them, and get predictions on images. Another nice thing is this declarative model spec. So no coding, just declare what your model is, press go. It's got a simple command line interface for training and fine-tuning. So yeah, again, you don't have to write much code there. You just it does all the magic in the background. It's fast. It's got a fairly small memory footprint, relatively. And also, one of the nice things is with Caffe, it's kind of hard a little bit to specify your own layers. You have to write them in C++ most of the time. But depending on what you're doing, you can actually do Python layers as well. So you can specify a piece of Python code that will do the forward pass in your network and the backward pass, and you can give that layer in your proto-text file, and it will use that. That's fine if you want to do kind of a custom loss function, for example, or you want to do a layer that gets data from somewhere, so say loads it from some specialized file or decodes video, and that'll work quite well. You probably don't want to use a Python layer right in the middle of your network, because that's a bottleneck, and that stuff needs to be done on the GPU. But for doing custom loss functions, things at the start or things at the end of the network, it's quite nice because it allows you to do it quite easily. The cons is it's kind of hard to install. There's a load of dependencies, boost, and all of the different sort of conveniences that it provides come at a cost. So just because it gives you, all of these things out of the box, LevelDB, LMDB, HDF5, you have to have all the libraries to actually work with them. So that makes it hard to install. It doesn't do automatic differentiation. I haven't even mentioned what that is yet, but basically some of the other libraries, you only have to specify the forward pass. So how to compute the loss. You don't have to tell it how to compute the gradients, right? It will figure out what the gradients are from you telling it how to go forward. That's automatic differentiation. And things like TensorFlow and Theano will do that. Caffe, you've got to do it yourself, right? And it can be easy enough to make a mistake when you're writing down the code for doing the gradients. And so that's a con. It's not so convenient to extend. It's written in C++. The code base is a little bit unwieldy, so it can be tricky to do that. It's a little bit less flexible than some of the other frameworks, and the Python interface doesn't expose all the functionality of it, so sometimes you really have to dig down into the C++ code. Something that's built on top of Caffe is called NVIDIA Digits. If you really don't want to touch code at all, then you can use this. It's a nice kind of web-based interface for training models. So you essentially give it one of these proto-text files, point it at your data. It will build the LMDB or LevelDB in the background for you. It'll train, it'll plot all these learning curves. It will allow you to visualize the filter outputs and things like that. So it's a really nice sort of way of understanding what your model's doing. So the learning curves that Ava mentioned earlier on will be plotted there, and you can watch them as your model is training and see if anything is going wrong or whatever. The other major sort of player from a while back in the deep learning world is Theano. So it's not really a deep learning library as such. It's more of a library that just allows you to specify these symbol graphs that compute arbitrary mathematical expressions, and then it'll optimize the execution of them symbol graphs. Often it will compile them and run them on the GPU, for example. So you don't have to write any CUDA code or anything yourself. You just say, what's the mathematical expression that I want to run, and it will be able to do that for you. And it will also be able to do the reverse. So if you give it any mathematical expression you want to optimize, and you say, okay, I don't want to bother computing the gradient of that myself, tell me the gradient, it will give you the gradient, and then you can easily implement stochastic gradient descent. Because it's like this, it's fairly low level, right? So you don't just say, okay, convolution, max pooling and things like that. You have to write the actual mathematical expression for it. But there are things, as I said, on top to make it easier. So yeah, it's very flexible as well and customizable, and it can execute on the GPU or the CPU. The pros of it, well, pro for me anyway, is Python. I'm a Python person. I like Python. Super flexible, supports automatic differentiation, has CUDA support, which is CUDA is the, well, I'm sure you all know what it is. It's library for GPUs by NVIDIA, allows you to do very fast execution in parallel. And it's got tight NumPy integration as well. So if you use Python already and you use NumPy, which is kind of a matrix library for Python, you'll find Theano reasonably comfortable. The cons of it, the main issue that people have with Theano is that, so I said before, you create this symbolic mathematical graph. You have to compile that, and it does some nice things for you. It optimizes out operations and removes things and reorganizes the graph so it runs faster. But that can take 5-10 minutes sometimes. And if you're testing lots of different models and you want to change things quite a lot, it can be a bit frustrating waiting 5-10 minutes for your model to compile. The other thing is it's a bit of a low-level API, so you really got to specify all the details, which can be kind of tedious. But there is things built on top to make that easier. So one of the libraries that's built on top of Theano is called Lasagna. This is what the code for Lasagna looks like. So basically, you can see that it's much more high level. You import your Lasagna and Theano, and then you say, okay, well, we've got some vectors we want to operate on, a 4-dimensional tensor, which is going to hold our data, and then we've got a vector that's going to hold our output y values. And then we just specify our layers. So we say, okay, we've got an input layer, then we do some convolutions on top of it, and then we pool them, and then we do some fully connected. So the terminology for this is a dense layer here. And each time you specify the parameters of each of these things, and then you can say, okay, well, we can create a function that will give us the prediction, and then it's got nice little things for. So I don't have to code out the cross entropy loss that we mentioned earlier on. You just call a function, and it's already written for you. So there's no point in recoding that yourself. It's there. And then if you want to train it, then you just run over your epochs, and you run over your mini batches, and you accumulate the loss, and you can print it to the console. So it's much more high level than so there we've got a full training procedure for a deep neural network in a handful of lines of code. If you were to do that in Theano from scratch, it will be a lot more code. So Lasagna is great because it's Python again. It's simple, so it has all these predefined layers that are easy to use. It's transparent as well, so it's only actually a thin layer over Theano, and you can get access to all of the Theano mechanics underneath it and all of the symbol graphs. So if you need to do anything more complicated, you can easily integrate it in there. You can say, okay, I'll get Lasagna to do a few bits, and then I'll take out the symbol that's resulting from that, and I'll do my own custom loss or something like that. It suffers from the same problem as Theano with the slow graph compile times. Keras is a kind of another one that's very similar to Lasagna. It's got a very simple torch-like model specification API. Torch is another deep learning library that you'll see now in a minute, written in Lua. If you've used scikit-learn, you'll really like this one because it's got these nice functions where you just say, oh yeah, fit my model with a fit function and predict and things like that. So it'll be very familiar for you. And it's a slightly different design philosophy to Lasagna. So Lasagna tries to expose the underlying details. Keras kind of hides them behind a backend. But one of the nice things about doing that is actually Keras can run on top of Theano and TensorFlow. So they just switch out the backend, that's no problem. This is what it looks like to specify a model, so it's even more terse than Lasagna. You just, this is a sequential model. There's two types of models actually in this. There's a sequential model where you just do layer output. And then there's something called a functional API, which allows you to define more general graph structure. So you may have two streams where your model splits out the data in two ways, goes down and then joins them back together. So the sequential model is great for just doing simple things, and then you have the full power of the other model as well. And then you call fit and predict and all of these things. So Torch is not Python. This is the Lua one. This is the one that's used by Facebook and DeepMind. Well, actually, DeepMind are moving to TensorFlow now. So, yeah, but so it's written in Lua and compiled with LuaJIT. So it makes it actually really fast. LuaJIT is 100 times faster than Python. Not that it makes much of a difference. Most of the computation is going to happen on the GPU anyway. So the cons of this is actually it doesn't have built-in automatic differentiation, so unlike Theano or TensorFlow. But there's a library called Twitter Autograd that implements this, so actually you don't really have to worry about it too much. It's not in Python, so you don't get all the batteries included. So Lua is a bit of a minimalist language. It's meant to be like embeddable and things, so it doesn't come with a big nice standard library and loads of packages, so you don't get all that nice stuff. TensorFlow is the new one from Google. I'm sure everyone's heard of it and people have had their tutorials on it already. It's similar in spirit to Theano. It's a simple graph-based approach. It's written in C++. It's got first-class Python bindings. You're generally intended to use it through Python. It didn't actually have distributed computing support at the start, but now it does, and that's great because if you want to run these things on multiple machines, you can do that. It's got very good documentation. It's flexible. There's no graph compilation step needed. These things are grayed out at the bottom because they're no longer actually relevant. So the earlier versions did have some problems, and you might hear people complaining about TensorFlow on the internet. That's no longer relevant. It doesn't have memory problems anymore. It's really fast in the benchmarks, so it's fine now. This is what it looks like to write TensorFlow code. I'm not going to spend time on it because you'll see plenty of this in the other part of the course. One of the problems with this is it can be a little bit verbose if you're defining big models. There's something called TensorFlow Slim that was recently released by Google, which is just a kind of a little layer on top of it, very lightweight layer. This is the VGG16 network. You don't know what that is yet, but it's a very deep, complex model. And here it is written in TensorFlow Slim. And you just basically say, okay, I want to repeat a 2D convolution twice, and then I want a max pool, and then I want to do this. So it allows you to get all the power of TensorFlow, but much more terse, less boilerplate. There's a bunch of other deep learning libraries, MixNet, sure. MatConvNet. So if anyone's a MATLAB fan, they'll probably want to use this one. I haven't used it myself, but I heard good things. Nirvana Neon, this is one that's really fast by a company. This is kind of a new one that's written in Rust if anyone wants to try something totally different. One of the nice things about MXNet is if you like any of these languages here, it's got bindings for everything. So kind of one of the final things to compare them. This is kind of grayed out now because this actually did matter when I first wrote these slides. There was differences in speed and all that. But they've all adopted the new CUDA library, CUDNN. So they're basically roughly as fast and use roughly the same amount of memory anymore. It's less of a consideration. Some of them have nice allocators built in, but it's not as big a deal as it was. If you want to choose between them now, really it's more of a what you like using, what kind of style of API you prefer. How much flexibility do you need? Do you want to write much code and things like that? So these are the kind of things that make a difference now. The speed and memory is not as big a deal as it used to be. And if there's a particular language that you want to use, then that will probably guide it. So yeah, just the last note on CUDNN. So that's what I was saying, that it's kind of leveled the playing field somewhat because this is the library that most people are using to train on the GPU now, and it's pretty fast. So, and all the major deep learning libraries that I've mentioned will support CUDNN. So yeah, the choice of a framework is now kind of a matter of taste. You guys have seen the kind of code that's there. You're free to go through the slides. If you want to ask any questions about these frameworks, feel free to do so.
Okay. So do you have a question?